Hi everyone, I'm Puneet and welcome to this session. Today we will dive into BFS, one of the graph algorithm, a fundamental concept for solving many coding problems. So here is what you will learn. So we'll learn what BFS is and how to implement BFS. Then we will take a sample question from Leetcode and solve it. So let's get started. So BFS is a graph algorithm, a graph search algorithm, where we start with a source node, and with each and every node we explore all its neighbors. So let's say we start with 0, then we will explore 2, its neighbors 2 and 1, and process these nodes. And then again we take its neighbors, let's say 1, and then explore all its neighbors. Then again take the neighbors of 2 and explore its neighbors. So BFS works in this way. So let's see in this example. So here in this graph, 0 is connected to 1 and 2, 2 is connected to 3 and 0, 1 is connected to 0 and 3, and so on. So let's say we need to find the minimum distance or minimum cost path between 0 and 6. And let's assume 0 is our source node. So let's start with 0. Let's process 0. So the distance of the source from source is 0. Then we will explore its neighbors 1 and 2. So distance of 1 from source is 1, and distance of 2 from source is again 1. So distance is, I think, or cost is nothing but we can say the number of edges in this case. Now we have explored 0 and explored 0 and process its neighbors. Now explore its neighbors. Let's start with 1. 1 is connected with 0, but 0 is already processed, so we'll not do anything. Let's process 3. Its distance from source is 2 via 1, and distance of 4 from source is again 2 via 1. Then let's explore the second neighbor 2. 2's neighbors are 0 and 3. 0 is already processed, and similarly 3 is also processed, so will not change anything here. So now explore using 4 and 3. So 4's neighbors are 3 and 5. 3 is already explored, so we will explore 5. So its distance from source is 3. Now explore the neighbors of 3. Its neighbors are 2, 1 and 4 and 6. But 2, 1 and 4 are already processed, so we process the 6. Distance of 6 from source is 3. So here we know we found the destination node, and we can say that the cost of path or distance of 6 from source is 3. So let's see how to implement it using a pseudocode. So we represent graph using adjacency list if you want to represent a graph using matrix. So here in the right hand side you can see adjacency matrix is a vector of vector or a array of array. So let's see what's the value for at the 0th index, or you can say what are the nodes connected with node 0. These are 1 and 2. Similarly for node 1, so 0, 3 and 4 are connected with node 1. Then again for node 2, 0 and 3 are connected with 2, and so on. We will fill, or we can say we can initialize all these values as per the connection in the graph. Okay, so here is the code. You will get the adjacency matrix, source and the destination to you as per this problem statement. So in order to implement the BFS, we use the queue because we need a data structure to hold all the neighbors of a node we are going to process next. So this queue, what this queue is actually having, it's having the node and the distance or cost. So we push the any source element with distance 0 from source, and now process the queue until it is empty. So we are taking the size of the queue because we want to explore all the neighbors of a node. So we'll see how it is working here. So let's say we added the source node here. We calculated the size. It's one at this point. Then take the first element from the front of the queue and pop it from the queue. We will check here if we found the node. Then we can simply send back the answer, the cost or the distance. Otherwise, what we will do, we will explore all the neighbors of that node. Okay, so let's say we added the 0 first to the queue, then the size was 1. So we actually in the queue node we get the first element of the queue, and it's not the destination because the node 0. Then we will explore all the neighbors of 0. So neighbors of 0 are 1 and 2, and we need to keep one more data structure to know which node we have explored so far. So we can take map, set, or any data structure of your choice to do that. What we can do, we can simply have map. We call it visited map. So here we have visited the source node. So far, yeah, okay. So we explore the neighbors of 0. Let's we get the first element like first neighbor as 1 is not explored, so we can add it to the queue. Now we updated the distance of this node from source. So we are actually exploring the neighbors of 0. So 1 will be at a distance of plus 1, whatever the distance of previous node from source. So it was 0 in this, so it will be 1 in case of 1, and similarly for 2. Then we will add both these nodes to the queue, and we'll come out of this loop, and then again queue is not empty. We will take the size, queue size now is 2. So we know that at first level we had the one node, so we need to run the loop once. At the second level we have two nodes, so we will run the loop two times. That's why we are actually taking the size and running the loop till the size. And it helps us to identify the correct distance for each and every node at that level. And during this process, when we will add finally 6 to the queue, we will actually pop it from the queue, and we will see that this node is equal to the destination. Then we'll send back the answer. So this is how we implement the BFS. Now let's take an example from Leetcode. So let's solve this Leetcode problem. So here what we need to solve here, you are given a 2D matrix, and we need to return the distance of nearest 0 for each cell. So basically we'll be having 0 and 1 only in this 2D array, and for each one we need to calculate the distance from the nearest 0. And again here, how to find the neighbors of each and every node. So neighbors of each and every nodes are its left node, right node, up and down. So let's say for example for this one we have four neighbors at, you can say, left, right, up and down. So let's solve it. So let's take the first example. So here is the first example. So here what we can do, we can actually add all the zeros to the queue. We will add all the zeros to the queue, and then we'll start processing in the similar way that like we saw earlier. So let's say we start with this zero. So its neighbors are this second element and the element down. But these elements, these are not one. So we can't do anything for this because we need to calculate the distance. If we see a 1, then we need to find the distance of nearest 0 from this one. So till now we explored two, you can say the two neighbors, but none of them are 1. So we'll do nothing. Okay, then come to this second node and we will see the neighbors. Neighbors are 0 and 1. Here we will see we find a node which is non-zero node. So what we can do, we can actually assume the distance of each 0 with itself is 0. Now we are coming to the second node here. So we can calculate the distance as 0 plus 1. So we can have 1 here. Okay, then if we start with this 0, then again we have the same situation. We are at the same situation. We have the two nodes, two neighbors, 0 and this one. But this is already processed, so we will not do anything. And similarly for other nodes, we will not update or change the distance. So this will be the answer. So let's see the answer of the first one. Yeah, it's again same as this node. So let's take the second example. Okay, so here's the second example. Here again we will do the same. We will add all zeros to the queue and then we'll start processing the graph. So let's say we start with the first 0. Its neighbors are 0, 0, so we'll do nothing. Then start with the second 0. Its neighbors are this 0 and this 1. So we found a node with non-zero nodes. We can update its distance. So it must be 0 plus 1, 1. Then come to this node 0. Its neighbors are 0 and this previous 0. So we'll do nothing. Okay, then come to the second row. This is the 0. Its neighbors are again non-zero neighbors. We found 1 and 1. So here, what we will do actually, we will not actually update this one because it's already processed. We have processed this already, and how to keep track of this we will see in some time. So, so there is another neighbor, non-zero neighbor 1. We can update the distance of this as 1. Then again, what we need to do, if we are actually processing any node, we need to add that to the queue as well. So there might be nodes that are not reachable via 0 that can be reached via 1. So we'll add this to the queue. Then again we'll explore this. Its neighbors are this 0 and this non-zero node. So we can update the distance of this one. This will be distance of this node from source is 1 plus 1. So it will be 2. Now come to the third node of this row and its neighbors are this one and this, and this one we have already processed, and we can update the distance of this node from this 0. So it will be 0 plus 1, 1. Okay, let's see. Yeah, this is the answer. 0 0 0 0 1 0 1 2 1. 0 0 0 0 1 0 1 2 1. So let's come to the solution. Okay, so we are getting this matrix as the input. Then we can have this x and y parameters just to calculate our neighbors, and we will take a queue to process the nodes, and we will add all the 0 nodes to the queue. So I will be updating the same matrix, but you can actually make a copy if you want. And for each one, we are making it as a -1 just to mark it as it is not processed yet. So I'll not be using any extra memory to know that it's processed or not. If you see a -1, it's not processed. So let's start our BFS until queue is not empty. Take the front element of the queue, calculate its neighbors using these. these vectors, these arrays. So what we are doing, just add the first element of this, like 0 to the x element, then the second corresponding y element, or you can say the whatever in the second array to the y coordinate, or the second, you can say the what to call this, second dimension of the array. Okay, yeah. And then we will calculate, we will get a neighbor of it. We just verify that it's not getting out of array bound. It should not be less than 0, and it should not be out of the memory, sorry, out of the range of this array, and it's not a non-zero. Also, it's not a minus one. It is not a process node. It is not a process node, then we will continue. So either it will be zero, or it will be a value that we have calculated. So we will not do nothing. So if it is not a zero, or if it equal to minus one, then we need to update the value. Then what we will do, we are actually coming from this node. We are coming to this node that we are calculate NRNC. What we can do, we can update the distance of it from the source from where we started. These are RNC, and then we will add that node to the queue as well, because there might be some nodes where we can't reach via zero. We need to actually get there using this processed element, and then finally we'll return this matrix as the answer. Okay, let's try to run this if it is working or not. Yeah, it's working perfectly fine. Okay guys, so we learned today what BFS is and how to implement it, and then how to use it for solving lead code problems. I hope this example questions gave you clarity on how to approach similar problems. So try solving some other lead code problems with the tag BFS, and let me know in the comment section how it went. And what is the biggest challenge you face when using BFS to solve the problems? Drop your thoughts in the comment. And if you need any help, if you have any doubt, you can ask that in the comment. I will try to answer. And also share this video with a friend who is preparing for coding interview. Thank you.